Alright, today we're going to talk about Archimedes Principle and buoyancy. Such a funny looking word. And if you know anything about Archimedes, it's where we get the word eureka and the connotations that we use it all the time. And this is why. This really long story, you can read it if you want. I'm going to give you the gist, or you can pause it and read it if you so choose. The gist was, there was this king who was given a crown, and they didn't think that the crown was solid gold, but they had no way to really test it because they didn't know about density and stuff back then. So Archimedes was like the king's personal smart dude. So he couldn't figure out how can I test to make sure this thing's solid gold. It racked his brains. So he decided to take a bath. And when he got in the bath, he had the water filled all the way to the top. And when he got in, of course, the water overflowed. And that's where he said, Eureka! And he realized that the volume displaced was equal to the weight of the water, or his weight displaced an equal amount of water. And he thought, oh, we can apply this to gold too. So he tried it with the golds and the crown, measured the water, put the crown in, and it turned out the crown was fake, and the other guy probably got beheaded, killed, or whatever, because you can't mess with a king. So basically, this is what happens when you drop something into a bowl of water. The rock goes in, the water level goes up. So this rock has some mass, and it turns out this volume of water is going to have the same mass. And this is where we get Archimedes' principle from. And it states that the weight of the amount of water displaced is equal to the buoyant force. So whatever weight, this water all has a weight up here. So the weight of H2O is going to be equal to the buoyant force acting on whatever object we place in it. So which one of these? So you see a ship. This is why ships can float, but a rock will sink. The ship displaces, it pushes down with some amount of weight, and because it's so big and the weight's spread out, the buoyant force is going to equal that weight. When the buoyant force equals the weight, something's going to float. If the buoyant force is less than the weight, though, the object's going to sink. So the boat displaces this much water, and that's equal to the buoyant force. So it has all this extra weight up here that, doesn't really matter. So here's some causes of why objects float. Causes: weight is less than the buoyant force. It's going to float. It's going to float if the object is less dense than the fluid. It's also going to float if the object decreases its mass and becomes less dense than the fluid. And it's also going to float if the object increases its volume and becomes denser than the fluid. And on the other hand, an object will sink if the weight is greater than the buoyant force, if the object is denser than the fluid, if the object increases its mass and becomes denser than the fluid, like we overload a ship, it might sink. Or if the object decreases its volume and becomes denser than the fluid. I think that last slide should be less dense. Less. Typo there. Less dense than the fluid. Now it makes sense. Object decreases its volume and it becomes denser than the fluid. Because we know if we ball something up, it becomes denser. If we take a piece of paper, not very dense, but if we ball it up, it's going to become denser. Alright, so suppose we weigh an object in air on this side. This guy's in air. And we weigh another object in water. How are these weights going to compare? So remember, buoyant force is equal to the weight of a fluid, of the fluid that's displaced. So this rock in the water displaces an amount of fluid, and the weight of that water displaced is going to equal the buoyant force. So it's because of this that the weight 1 is greater than weight 2. Because on this guy, we just have tension going up, tension, and weight going down. But in this guy, we got tension going up, we got weight going down, but we also have the buoyant force pushing up. So because we have two forces here acting upwards and only one going down, this W is going to be a lot smaller. So since the pressure at the bottom of the object is greater than at the top of the object, the water exerts a net upward force, the buoyant force on the object. So pressure is greater down here, it's pushing up on this guy, that's called the buoyant force, and it decreases the weight of this object. So you weigh yourself in the pool, you're going to weigh less. So the buoyant force is equal to the weight of the liquid that's displaced, we've already said that. So if the buoyant force is larger than the weight of the object, it will float, otherwise it will sink. Just restating this stuff because, repetition is, part of learning. So we can calculate how much of a floating object will be submerged in the liquid. So if the object is in equilibrium, just floating there, like this guy's floating right here, then the buoyant force equals the weight. Makes sense. If buoyant force equals the weight, there's no net force, object's in equilibrium, acceleration equals 0, it's not going to move anywhere. And here's a formula we derived in the last podcast. The density of the liquid times gravity times the volume of the liquid displaced equals the density of the object times gravity times the volume of the object. And we derived that formula in the last podcast. We can rearrange this. We got g's on both sides, so they're gone. So we have the volume of the liquid divided by the volume of the object equals... those are backwards. Oh, no, we're good. Volume of the liquid divided by volume of the object equals the density of the object divided by the density of the liquid. So it's easy to solve for one of these if we know the other three. So here's a couple thought experiments. So what's going to happen to the water level when this ice cube melts? It's already displacing a volume of water equal to this guy's weight. So it's actually going to stay the same. However, what if we put a rock on top of that ice? Now, since the ice cube and the rock weigh more together, they're going to displace more water. It's already going to initially cause the water to rise a certain amount because it's only the weight, the mg going down, that's displacing that water. So again, it's going to stay the same. Alright, so we have 5 blocks, all have the same volume. Block 2 floats with a little bit sticking above. Block 5 sinks all the way to the bottom. What's going to happen to these other 3 blocks whenever I drop them into the water? If 1 is the smallest mass, 5 is the largest, and they go up in order 1, 2, 3, 4, 5. Alright, you might think that this would happen, but you would be wrong. So this is more likely to happen. 1, it's going to float a little higher than 2. That's a little obvious since it has less mass, so it's going to float. But because 3 has more mass than 2, it's going to be more dense than 2. So it's either going to hover right here in the middle or sink all the way to the bottom. Now 4, it's pretty much going to go all the way to the bottom. And 5, it's already on the bottom, so it's going to stay there. Alright, here's something else you can try at home. Take a small lead weight and you put it on a piece of styrofoam. And if you put it in water, the water is going to just barely touch the top of the styrofoam, and the lead's going to be sitting on top. If we turn the styrofoam and lead upside down, what's going to happen? Is it going to be completely submerged like this, going to float a little bit, or is it just going to be the lead weight on the bottom, the styrofoam on top? So we're going to assume the density of lead is greater than water, which we don't have to really assume because it's true. So actually, this one's going to happen. The lead's going to pull that styrofoam down. It's going to be basically the same height that it was before, but a little bit higher since the styrofoam is less dense. It's going to push it up a little bit. One more thing, a little example. So 2 identical cups are filled to the same level with water. One of the 2 cups has plastic balls floating in it. Which cup weighs more? They're actually going to weigh the same. That's because each one of these blocks has a weight pushing down, but it also has a buoyant force pushing up. These guys cancel each other out, so it doesn't affect the weight of that cup at all, because the buoyant force and the weight of each little ball cancel each other out. So remember the last podcast I said we can figure out why the Titanic sank, like why it hit this ginormous iceberg, you know, all you see is like this little chunk floating at the top. So according to Wikipedia, because the density of pure ice is about 920 kilograms per meters cubed, and that of seawater is about 1,025 kilograms per meters cubed, typically only 1/10 of the volume of an iceberg is above water. So if you divide 920 by 1025, you're going to get about 9/10, so 1/10 difference. So that's why we only see the very tip, because icebergs are pure ice, pure water ice, but they're salt in the seawater, so it's a little more dense. So the iceberg is going to float, but it's only going to have 1/10 of its surface above the water. So if a very large floating iceberg were to melt, oops. So if a very large iceberg were to melt, it's not going to change the level of the water of ocean. Like the ocean's not going to rise if that iceberg melts, because that iceberg's already displacing water. It's already pushing water upwards. So if it melts, it's just going to stay the same height. Now, why people are worried that the ocean levels are going to rise, because the ice shelves, chunks of ice like on land, are falling into the ocean, and they're going to keep doing that. They're going to increase the level of water. That's why global warming is bad. So here's the reasoning behind that. So when an object is immersed in a fluid, the fluid exerts an upward force on the object equal to the weight of the fluid displaced by the object. So iceberg not melted has weight W and volume V1. So it places a weight of water with a volume of VW, which is less than V1. So it floats. So some of the iceberg sticks up above the water. So VW is actually less than V1. So an iceberg melted has the same weight and less volume, but it still displaces the same amount of water, and it still displaces a weight of water W. So these W's are equal. The weight of the water displaced by the iceberg and the weight of the water that's displaced are equal. Now, but when it floats, this VW is going to equal this V1. So melting an iceberg, which is floating, does not change sea level. So if the iceberg were not floating but sitting on a landmass and it melted and added water to the ocean, this would increase sea level, and everybody living on islands or close to the ocean would drown. And that is all.